So thank you all for joining. I will also try to, well, maybe address you and the audience live as well. I'm currently working at IMEC, and IMEC is a research institute for nanoelectronics. I've been in Louvain and I've been in Leuven and in Karlsruhe. But this is like an institute that is sort of in between the academic world and the industry. And it is effectively a world-leading institute for nanoelectronics. When I started there about 3 years ago, it existed about 30 years, originally as a startup from the university. And by now, there were at that point some like 4,000 researchers. And in the last couple of years, we went from 4 to 5,000. So we're growing very hard. The headquarters is in Leuven. Lots of collaborations in Flanders universities. We have offsite locations in Europe and USA and in Asia. And we do a lot of modeling. Modeling going all the way from the ab initio level to the full device level. Coarse graining and thermal dissipation in entire chips, for instance. And our core ab initio group currently consists of about 5 permanent people. Most of the time we have about 6 PhD students. IMEC-wide, there's about 800 PhD students working, and we also have some industrial residents, people joining from other companies that do their research in our group with our support. But then there's a lot of other people doing ab initio research on specific topics that are basically affiliated to our group. The research is actually spanning lots of different topics, and I'm mainly working on CMOS and beyond and memory systems, and also on understanding photovoltaics and lithography. And all of that comes with a very large and impressive, I would say, range of experimental facilities. Now, just to have a little focus on 2 topics that I'm currently working on, and one of these is actually screening of new materials, which is quite close to a lot of the topics that we are seeing here. And this you can imagine, we have like systems to 200 to 400 atoms in a cell and thousands of them. But what we're interested in here is optical properties and electronic properties of these big systems, not crystals, but amorphous materials. The other topic I'm showing down here is actually photoresist chemistry. It's maybe even more complicated. To actually get a structurally sort of correct picture of what's happening there, you need a unit cell of about 22,000 atoms. And to get statistics proper, you need at least in the order of several thousands of different structures to study. And then to make things worse, right now we're looking at EUV lithography. So we want to understand what extreme UV photons do to this material. And that's photons of 92 electron volts. So you can imagine these are very, very big challenges. So the main challenge, I would say, is that we have very large systems and that we need a very high level of accuracy in our calculations. What kind of tools do we have available for this? Obviously, a lot of the work we do with density functional theory. Obviously, for those complex systems, we usually start even with force fields to get our first impression, but then we usually switch to DFT. DFT is nice, right? Main core thing that makes it happen is that it maps the complex many particle problem into a single particle problem, makes that systems up to 2,000 atoms can be readily dealt with. And it's broadly used, but the main problem is that exactly those electronic levels that we are interested in, charge transfer, long range interactions, and especially band gaps, are not so accurate. So fortunately, there's a solution to this, which is the GW method. That's mainly what I'm going to talk about today. And what happens here is basically that this exchange correlation potential that is used in density functional theory to map this many particle problem into a single particle problem is replaced by a somewhat more complex object, but a complex object that we know how to make approximations for, and that makes that our theory now has more predictive power. So in this method, we basically get a description of electronic levels that makes sense, that actually has a meaning, and it usually fixes our band gap problem. And this was the state a while ago. So GW came around, people started first tries comparing a few solids, and GW solved all the problems, right? You see the LDA, like the DFT level calculations, you have a gross underestimation of the band gap. And when you do GW, all the problems are solved. And a couple of later, people redid calculations and all the problems weren't solved anymore that well. But then obviously, good, we can solve this as well because we can go to self-consistency. But then the question is obviously, what kind of self-consistency? So basically, there was all these kind of different results coming up. So you can basically ask you a lot of questions. How precise are the results? How accurate is GW in practice? And is there any hope to kind of completely automate it? Because in terms of cars, GW is still far away from our current fully automated cars that have lane assist and cruise control. So there is an endless list of questions. Right? What kind of GW should you do? What kind of starting point do you need? What kind of level of self-consistency? What kind of integration method? What to compare to? All of these things are basically questions that you should answer before you can use GW in a very systematic way. We heard this already in the introduction that Xavier gave, right? So you could think maybe it's a new method. So it may actually be that this method still needs some development. It's actually not a new method. It's almost as old as DFT itself. So it's 1995 that Lars Setten wrote down the equations. And then I think the first actual calculations on materials were a couple of years later, but like 15 years later, right? And then it took another 15, 20 years for GW to arrive in like publicly available codes. And then it takes more and more time. And then only like 50 years after the first kind of description of the methodology, words like predictive and benchmarking and reproducibility start to appear. So the question is, do we care too little about reproducibility or what, right? And if you look at it, you just heard an excellent talk about this. Reproducibility really investigated, even for DFT, is already a very hard nut to crack, right? And then it was only done for just the elemental systems, and we're just moving away from elemental systems to oxides, but not for hybrid functionals and not for defects in these materials, right? So there's lots and lots of work to do. So maybe doing all of this for GW in a consistent way is just a very hard problem. So with that in mind, we thought, look, for solids, this is still a very tough problem. Maybe if we just take it a little bit easier and we go to molecules, it may be easier to do. And this is basically what we did. It took a couple of years. And in 2015, we finished this project and we basically had 3 different codes sort of agreeing on the ionization energies and electron affinities for 100 different molecules. I'll show you which molecules there are and then more information on this. So this was 15 years, this was 2015. And in the meanwhile, actually quite a lot happened. And that's something I'm quite proud of. From these 8 different HOMO energy data sets, a couple of days ago, I added a few more from the ADF code. And by now we have almost 150 different data sets available, all following this calculational setup for these 100 molecules. So now we can really start doing very in-depth analysis about all these different approximations and what is happening in these codes. So in the meanwhile, we got coupled cluster reference results. We got results from FASP and from WESP and from CP2K and from stochastic GW, MOL GW, Fiesta, Nano GW, Abinit, Jumbo, Vodka, and last month ADF. So really a lot of things happening. On top of that, we have been going also to accuracy, different kinds of self-consistency, different kinds of starting points, but also other projects are using this data set now. Projects that also calculate HOMO energies and ionization potentials, but not necessarily with GW. And then later, just recently, it's almost out. We even have other perturbation theory results now. So all of this is now put together in sort of a joint data format. So we have one data format where people can contribute their data, their results. And then there is all kinds of toys and tools to compare this, to visualize the results between two different codes. All of this is part of a Git repository where you can basically download the tools and commit your data. So just to give you a little overview, and this is probably the weakest point of this data set. These are the atoms that are currently present. Doing this for the transition metals was already, we only have 3. Extending it will be another nut to crack, but right now this is the situation we have. The first motivation for us to kind of start making a new set was sort of similar to the previous talk, that we wanted to annoy the atoms a bit, right? Quite often in quantum chemistry reference data sets, you see a lot of hydrocarbons and not too many complex things. So here we added some little metal clusters, hydrides, oxides, and very ionic type of materials as well. And that actually means that you kind of go into the extreme and you notice the harder differences. So in view of what we've been talking about, I will now talk about 3 different topics: reproducibility, precision, and accuracy. And I will just keep to exactly the same definition as Xavier introduced in this section, and we will start with reproducibility. So it means that when I do the same calculation with 2 different codes, but that in principle do exactly the same thing, do I then get exactly the same results? Well, this is a nice thing. We have 2 codes here, my implementation in Turbomol and implementation of GW in mol GW by Fabien Bruneval. And we can use exactly the same basis set, and we use exactly the same way of doing GW. And this is the kind of agreement that you can then do. I said exactly the same basis set. There's a tiny little difference in the auxiliary basis set, and that's giving rise to these little outliers. But you can see we're here, except for 3 systems, we are within 10 millielectron volt accuracy. Oh, precision, accuracy. And now we can continue, right? We can collect all the data from our entire big data set, and we can compare things, right? So this is all the results calculated at this QZVP quadruple zeta valence plus polarization basis set, where we do exactly the same GW. We do G naught, W naught starting from PBE. We try to do the best thing ever. And you get a comparison between all these codes. And then we can start looking at results for different kinds of approximations in the part of the calculation of the GW, right? And this is basically comparing what happens in the Padé approximation, one of the most famous approximations that you need to make at some point to calculate the integral between the GW or between the Green's function and the screening. So you can see if you do this in a crude manner with only 2 poles or a very automatic scheme, you kind of get deviations up to 1/10 of an electron volt. But if you now do this very accurately, you go from a 2-pole approximation to, for instance, you expand your Padé expansion all the way until you really reach convergence. You actually see that for this HOMO energy, effectively you converge to the results that we have from the fully analytic approach. So now that we have established that if we kind of use 2 codes that do exactly the same thing, especially if we use the exact same basis set, that we get the same results, what about precision? Right? And precision here is all the errors that you introduce in your final result by having numerical and mathematical approximations. So nothing about the physics yet, but like the process of kind of putting your continuous problem in a discrete problem on the computer effectively, right? So basis sets are a part of this. So here we can take our local orbital codes and have a look at the convergence in the basis sets, right? So we have single zeta, triple zeta, quadruple zeta, and an extrapolated version of the results from triple zeta to quadruple zeta to extrapolated results. And we now get, let's say, a number on how accurate, how precise are we in a specific basis set. And just for everyone who's not very familiar with these basis sets, for standard DFT calculations, most of the time your triple zeta is really already a very good basis set. You hardly ever go beyond triple zeta if you want to do DFT calculations. But you can see here, for GW, even the quadruple zeta still is off by 0.1, 0.2 electron volts. I can do the same thing for the LUMO energy, and there it's a lot harder to get really converged results. But now the real question obviously arises. Right? Until now, we have only been talking about comparisons between local orbital codes. Let's see what happens if we start comparing now local orbital codes and plane wave codes, right? Completely different philosophy in how to make your basis set. And the main message that we learned here was you have to do a very systematic extrapolation on both sides. And if you do that, then effectively you get to a situation where you have a very decent agreement. Very decent meaning your results for like a very large set of the molecules are within 0.1 electron volts, but we still have some outliers here and there. So if you do the extrapolation of your basis set carefully, you can get agreement between the codes. And then we can look at all kinds of other computational details, and we can see how well things converge and which code gives what results. Finally, this is let's say a summary of the codes that we currently have split up in terms of local basis sets, plane wave basis sets, whether the results are extrapolated or not extrapolated. So effectively, we can derive some numbers on how accurate is my calculation. So that basically puts now the question of precision under control. So finally, once we have reproducibility and precision under control, we can start looking at accuracy. And accuracy is effectively if my calculation is done in the end, how well do I describe the experimental value? Or how well do I describe the result from a level of theory that is supposed to give us the best result? Now there is a difficulty here, right? And Xavier already talked about this 0-point energy, right? This is something that is inherently not available in the GW formalism at all, right? So there's no reason for me, I would say, to compare to experiment because it's always there. And we cannot sort of remove it very easily if we look at molecules. So the choice here is made to effectively try to compare to coupled cluster. And in coupled cluster, which is often quoted as the golden standard in quantum chemistry, you calculate these ionization energies not by looking at energy levels, but you calculate just the total energy difference between the neutral and the ionized system. And even this is already not easy, right? As you can see here, this is all the 8 data sets that we currently have in the GW project reporting coupled cluster results. And the top 2 are actually complete coupled cluster results, and the 6 below are already approximations on top of that. But you see that this is actually moving down. The 2 on top are the complete GW with perturbative coupled cluster with perturbative triples in the expansion. The original set was the one, the C4 results. And it turned out there were a few systems there that were actually a little bit off. And very recently, we made a recalculation of these numbers. And it actually turns out that a lot of the outliers you, for instance, see on the right side, when we take on the left side, when we take this, when we take on the right side, sorry, the original reference, there's a lot of outliers in the other codes. If we switch the reference to our new set in the left figure, we see we get a better agreement already for the different coupled cluster results. So in the remainder of this, I will compare the different GW approaches to the new corrected coupled cluster results. So the first thing we can look at is starting point, right? So GW, when we talk about this G0 W0, we basically do only a single perturbative correction on the Kohn-Sham or the Hartree-Fock energies. So when I go here from the top to the bottom, I go from pure Hartree-Fock all the way down to pure PBE. I decrease the amount of exact exchange that I have in my starting point. And you see there is a very nice, clear trend when I go GW on top of this, and I move from one starting point to the other. And then we can add self-consistency, and we actually see top and the bottom is no self-consistency whatsoever. The top is still Hartree-Fock and the bottom is still PBE. So we go from 100% exact exchange to the bottom. But now we have in between a bit of self-consistency. And you see that self-consistency still is not completely free of starting point dependence, but it reduces the starting point dependence a lot as compared to the G0 W0 results. And then we can take all the kinds of self-consistency methods and levels that are currently available. I think there's hardly anything left that is not yet already in our data set. And we basically kind of can make a few conclusions. If we then look back at our reference, then we basically see that either eigenvalue self-consistent GW starting from a hybrid functional that has a lot of exact exchange, 50% in this case, or we just do a G0 W0 on top of a hybrid functional with 50% exact exchange brings us closest to our coupled cluster results. And then finally, as I told you in the very beginning, there's also many other projects that are now starting to use this data set to compare their approximations for the ionization potentials to the coupled cluster results, basically. And we get this very long list of all kinds of methods that you can use to calculate this. All have different speeds, all have different computational costs, different memory costs. And effectively now with this evaluation, you can kind of pinpoint what is the accuracy of any method to calculate your ionization energies. So here's just another summary of the results that we have for these systems. And finally, I come to this slide. I would like to thank everyone who has been contributing to this project. I basically list all the authors of all the different papers and all the different contributions in chronological order. People in bold are people that contributed data sets that have not yet been published. And I think for this conference as well, the interesting thing is the people in blue. And people in blue actually have been contributing the data in the defined data set, right? A lot of the other data I had to go into the PDFs and kind of copy paste their results back out of the papers. But the people in blue actually got the point, right? So they downloaded the Git repository, downloaded the data format, and contributed their data in the proper way. So as you can see, as time goes by, we're getting closer to uniform databases. So I think that's a very good point to end up with. So, and then finally, on the right, you have a summary of all the institutions and codes that are currently represented in this project. So, and with that, I will leave you with the slogan of IMEC, and thank you very much for your attention.
Thank you very much, Michiel, for this nice presentation. So I'm looking at the audience here. Some question. Nothing here at the level of the question in the audience at large. Nothing. Good. So I would like to ask a question. What do you foresee as the future of this GW100 project? You have shown very nice results, self-consistency is now examined, etc. What do you think should be done next?
So I think the next thing is that we get more elemental diversity, right? So effectively, all our molecules are main group elements, right? Mm-hmm. So we have main group chemistry, and the real challenge would be to really go and include effectively all the transition metals in one way or another. That's the next thing we basically need to do. So I think sort of started on this already, but that puts another big load of complexity and adds another data set. So I think that's the next thing we need to do. On these molecules, I think we are pretty much reached the point that we can achieve.
Okay, what about the spin orbit coupling? Do you at present you focus on the scalar relativistic calculations, I think, and in the comparison with experimental data with increased number of atoms, will you address the spin orbit coupling as well?
I think that's a very challenging topic, and I'm not sure whether we can do this properly as of yet with the current implementations as much. So I think that's even further in the future.
Further future. Yes.
Most of the calculations are all electron with no relativistic effect, no scalar relativistic, nothing.
Exactly.
No, nothing. No. It's pure Schrödinger equation. Maybe just for the 2 or 3 elements that have a pseudo potential. So inside the pseudo potential, you have hidden there some scalar relativistic effect. But for all the other ones, they are just all electrons, pure Schrödinger.
Yeah, but that's for the local orbital code, right? So when you do the calculation with WASP or with BEST, or I guess also CP2K, and then it becomes very difficult to say more. But the plane wave codes in general do have relativistic corrections already in there, right? But you're completely right. So in the local orbital codes, that's basically also the decision that we took in the beginning here, to just exclude this for now and try to make, I mean, this was already very tough.
Yeah.
To do this at this level and to kind of make as clean as possible, to really decide we take this in this way and kind of extremely cut down on approximations.
Yes.
You've indicated that you can take also into account very large unit cells of 1,000, 2,000 atoms. So does that open also then the way to start treating interfaces? I mean, that must be something of interest to IMEC.
Yeah, so that is obviously right. So this was a topic where we have been benchmarking one of the computational approaches for like very accurate electronic structure calculations. In my current daily work, unit cells and systems are big. They're always big. They're complex. You have amorphous materials. And we have a lot of work going on where we have stacks of material with lots of interfaces, the fusion of elements. That's indeed in DFT we can do this. And there are developments here as well. For instance, stochastic GW and CP2K as well. They implement ways of doing GW that could, in principle, if you add enough computational power, take GW to systems of like several hundreds of atoms. But then you're talking about single system, single calculation on a very serious supercomputer. So we can take this methodology to that level. And since we now know what is the accuracy of those approximations, we know kind of what to expect from that. But it is indeed what we are mainly interested in. Right now in the level of nanoelectronics, everything is about interfaces and finite size effects of the thinness of your structures and your layers.
Okay, thank you. Oh, there is even one more.
From the yesterday, I noticed that you are experimentalist. Maybe I'm
No, I'm purely theoretician.
okay.
Yes.
So, but my question is that you started to work on molecules and distinguish this GW and everything on molecules. So, do you have anything in your mind that you are going to somehow compare your results, your more or less exact results with the experiments? Or I'm wondering, of course, beside the computational cost, if you want to, somehow investigate the solid states and with big unit cell and so on. I mean, beside of this computational cost, but why did you choose to study GW and molecules?
So as you will see in the next talk, right? benchmarking on solids is even more complex. And this work started quite a while ago, and we kind of put the foundations there to move towards more complex systems, right? There's so many approximations in GW that were made that you needed small systems to start with to get a very first grasp of what's going on. And I think that's been done now, and now we're gradually moving to solids for that sense. And when you talk about comparing to experiments, that's just the point we want to have as clean as possible. We want to look only at the electronic effect, not at vibrational effects, not at temperature, and not even at relativistic, right? That's where we made all these kind of clear-cut decisions to kind of look only at that level of theory. Thank you.